So I'm Zili Zheng from Lawrence Berkeley National Lab, so it's one of the DOE labs. So today I would like to share with you some of the exciting work we have been doing with UPC++. So UPC++ is a library-based PGAS probing system. As you can infer from its name, so it has some relationship with UPC, but UPC is based on C. And at least in DOE, there is an increasing demand of using C++. Many of our big applications are written in C++ and Fortran. So that's why we want to bring PGAS to C++, so that our application users, they can take advantage of the PGAS features available. But in addition, you have heard of APGAS, some asynchronous features that are coming up in other languages. So we want to support those as well. But in this case, we are putting those features in C++ instead of introducing a new language, because we understand that by using some familiar language can lower the barrier to entry. And also, we learned lessons from an old PGAS language called Titanium, which is a Java dialect. But in these days, as far as I know, very few people use Java for HPC. So we want to bring those lessons learned into C++. By working with some application scientists at DOE, we understand that it's really important to make sure whatever we do can interoperate with existing models such as MPI, OpenMP, CUDA, because there are diverse application needs and also different system architectures we have at DOE. Based on C++, as I mentioned before. So let me give you a little bit more details by a pictorial summary of what we are doing in UPC++. So we started with the PGAS model. I'm sorry, because I only uploaded the PDF, so all the animation is gone, so ruin is a pi factor. But we started with a private address space for each of the processors. So you can still do things like you can do with MPI. You can communicate by message passing, collective operations, so on and so forth. But on top of that, you see the blue global address space. And that's basically providing a shared memory abstraction on top of distributed memory. So users can conveniently do RDMA, basically, to and from anywhere in the system. That's convenient, especially for irregular data access patterns. But that's sort of the OPGAS. Recently, people want some doing things like dynamic task executions, also other high-level distributed data structures, and that's why we also put those into the PGAS model. For example, we support moving tasks to the owner of the data instead of moving data around. And this is sort of in spirit similar to active messages. We want to make it more user-friendly, because if you remember in Paul's talk, there are some restrictions about how you would use active messages. But for end users, they want to basically do anything with this remote procedure calls. For example, calling MKL, FFTW, even calling CUDAs. So we do want to support those and making certain design trade-off in the system software implementations. So next slide. I do want to talk a little bit about how we implement UPC++ and why we are doing that. So in UPC++, actually, we are not implementing a compiler. So for many of the PGAS languages, they do require new compiler, especially a front end to parse the new syntax and so on and so forth. But in UPC++, we decided not to implement it as a full compiler. Instead, we use a technique called C++ metaprogramming to sort of provide a syntactic sugar for a PGAS view for language. And the reason for doing that is that if you know the development cost for supporting a full production level compiler is very expensive. Even for C, over 15 years of our experience of developing a UPC, there still bugs exist today, and it takes a lot of effort just to maintain a state-of-the-art C compiler front end. And not to mention C++, especially C++11. As far as I know, there are only a handful of production quality C++ front end available today. Clang, GCC, and those based on EDG, including, for example, Intel compilers and many others. So that's why we believe it's best for us to focus our energy into the place where we believe we can offer some unique values. So we use C++, use template metaprogramming, but we give users the feel of language syntax, as I will show you some examples. And then finally, we link with a runtime library written in C++, which is built on top of GasNet. And then GasNet use all the system libraries on particular systems. So we do use OFAT and OFI conduits whenever available, but just in an indirect way. Okay, let me give you one example of what a code example of using UPC++ look like. I'm not sure if you ever see or read a UPC program, but basically it provides a shared memory abstraction for distributed memory systems. So in this case, we declare a big shared array that can be distributed across the whole system beyond any physical memory boundary. So that's very convenient. In C++, we use a template to do that, and it's nothing special. Just declare a big table, one-dimensional table, which can be terabytes, whatever the system can fit. I think the key thing is here. Now, when you access this table, this data structure, you don't have to do things like send or receive or even puts and gets. You just directly write it as you would for shared memory systems. You just write expression, right? Highlight in red there, table, and doing XOR operations. Of course, this is just a benchmark, doing nothing but random access. It's not very useful, but it shows how elegant if you can do things with the PGAS programming model. And the underlying physical layout is specified by the users. In this case, it just basically use a very simple cyclic layout. So all the data are cyclically distributed across all the network. And for the data on the same node, they have the same color and they are stored contiguously. And also we use terminology very similar to MPI. For example, ranks to tell you how many processors you have and my rank, so that again makes people feel more familiar with when they try to use our tools. Okay, one more thing. Now the share arrays, those are arrays, but you may want to build other data structures using pointers, basically like C or C++, and that's why we support the global pointer concept here. It's similar to the pointer to share in UPC, if you ever know, but basically what we store in the pointer is really global pointer. It's basically a rank and a local virtual memory address. And with that, you can specify any data, any memory location within the whole system. And we can support dynamic global memory allocation. So basically, you can say, I allocate 2 megabytes memory on rank 512, something like that. And this is, as far as I know, again, you won't be able to do it in MPI, at least not in the current implementations, because it requires active message support. Okay, one more thing about one-sided data transfer. Again, here we use RDMA to do the data transfer, but we want to provide a C++ interface for that and make it a little bit easier for users to use that, because our customers are mostly DOE application scientists, so they don't want to deal with things like registering memory regions or creating queue pairs, things like that. They should want to do something similar to what they would do with regular C or C++, mem copy, copies, things like that. Non-blocking copy is okay, but not too complicated. Okay. Now, next example I'm showing here is making a remote function call. It's really similar to what you would do with a regular function call, but except that you would add some prefix there. You're calling async and make a remote function call. This is much simpler than you would do an active message, because we're basically doing some syntactic sugar to hide the complexity of serializing some of the arguments behind the scene using C++ 11 variadic templates, sort of features to do this for you. And this become very powerful because you can imagine that now we are only printing a number. It's not useful, but you can call dgem, you can call fftw, making other function calls on any place of the data, and then you don't have to move the data around. Next example is something a little bit more syntactic sugar again. If you use a new language like X10 or Chapo, you will see syntactic sugar like finish. You can basically scoop a bunch of asynchronous text together. And again, we can actually do that within C++ without any new compiler support. And you can mix it with lambdas if you like to use C++ feature like lambda. Okay. Next is multidimensional arrays in C++, UPC++. So C++ does not, even C++ does not have very good multidimensional array support. And for many scientific applications, we do need that. So I'm not showing any code here, but just want to show you some cartoons basically saying that we allow users to use an object-oriented way to manipulate moving the arrays around, just like you would do with MATLAB. But in addition, we want to support a distributed memory system. Okay. So next, based on the multidimensional array that we build in UPC++, we provide a distributed array matrix abstractions. In this case, you see the distributed array can be very big, can be distributed across the whole system. And what's more challenging here is that each patch of this global array may not be of the same size. And if you want to do some updates from local to global, you may actually require doing updates and communication to several processors. But by using our library, you can hide all the complexity behind the scene. We also do other optimizations, such as using atomic operations if the hardware support those. And this can make our application run much faster. And we'll give you one specific application example. This is a Hartree-Fock example. That's a component in NWChem, a computational chemistry code. So in this case, we run our implementation with two examples and compare against with the state-of-the-art GT4 algorithm implemented by Georgia Tech. And by the way, that implementation actually won the IPDPS 2014 Best Paper Award. So we are basically comparing the best algorithm available. But we show that by using some system software optimizations, using some high-level data structure optimizations, we can even push the performance further and 20% better. And by the way, we also have some global arrays experts as our co-author. So we make sure that our comparison is fair and to the maximum possible extent. And it scales all the way to almost 100,000 cores on Edison, which is a Cray XC30 system at NERSC. Now, just also a very dense slide to show you another application example. So this sort of a global matrix update data structure not only exists in computational chemistry, it also exists in other applications such as SEISMIC tomography. So in this example, our collaborators at UC Berkeley use UPC++ to implement a global matrix update for reconstructing the images from seismic simulations. So the top graph, the figure graph, the performance graph on the right shows the para efficiencies up to 12K cores on Edison again. You can see it's almost flat, performance is gray, but getting performance is not the primary goal here. The goal is to help the scientists to solve new problems, and they actually use the tools to solve new examples that they have not been able to solve before, and that led to some publications in Nature and also won the NERSC 2016 Achievement Award for Innovative HPC. And next, I want to share some thoughts about the comparisons between the mechanisms we offer in UPC++ and GasNet with what you already have in MPI. So in essence, the computations that we are doing, the communications pattern is similar to MPI accumulate, but the difference is that using active messages, we basically allow the users to execute arbitrary functions, arbitrary tasks on the remote node. But in MPI accumulate, you're basically doing some predefined operations, but with general data types. And by allowing the users to do arbitrary functions, actually we expose more opportunities for the users to tune their applications. Of course, that also requires the users to understand the underlying stuff a little bit more. But using UPC++, the users can do explicit buffer management, customize their updates, and make progress calling pool whenever they feel it's the best, and save communication whenever possible. In contrast, if they just use MPI accumulate out of the box, lots of the things are just hidden, not controlled and not exposed to the users. So sometimes they cannot get the best possible performance. Okay, so last I want to share with you another real examples. In DOE, lots of applications are based on a numerical method called adaptive mesh refinement. The acronym is AMR. So AMR is a numerical technique that allows the user to dynamically focus the resolutions to the regions where of most interest. So it's like taking a taking pictures with a digital camera. You want to zoom into your object of your interest. But this flexibility also creates challenges for communications, because as you can see from the examples, the grids of the computation might not be regular. You may have some weird shapes of your objects. And because during the computations, it requires communication between final grids and coarse grids. So you cannot predict this a priori, and you cannot do this at compile time analysis. So that's why it requires communications between levels and also among neighbors within the same level. And the goal of our case is to try to use PGAS RDMA to optimize the performance. So the specific code that we are looking at is called BoxLib. So it's a production software developed by LBNL, by application scientists. It's an AMR framework, so which means that applications can be written on top of BoxLib. So typical applications including seismic modeling, combustions, astrophysics, so on and so forth. It's a representative of some of the DOE problems that we're trying to solve. It's written in C++ and Fortran 90 using MPI OpenMP. So before we get started, we try to get some understanding about the code base. So we run just slog count on it. It estimates it would take 70 years to rewrite it. So apparently we don't have the resource, manpower to do it before exascale systems. So that's why we believe an incremental approach is very important. Basically, we have to make sure whatever we do interoperate and work with whatever they already have. And we do this by collaboration with the application team. So next, I'm showing one specific example of how we change the communication pattern in BoxLib and using PGAS to help make the workflow simpler and also the performance better. So the original communication pattern in BoxLib is like the following. So a processor, I simplify this a little bit, because in reality you may have thousands or hundreds of thousands of processors. But in this case, we have only 4 processors, and P2 needs some data from P0. But the challenge for the two-sided communication pattern is that P0 does not know this. So it's hard for P0 to pose as a send for the data request. In order to communicate for the request, first of all, the application needs to do an MPI all-to-all to communicate within all the processors. Basically, it's trying to tell everybody else, do I need to communicate with you or not? In this example, you can tell that this is a little bit wasteful because P2 only need to tell P0, I'm going to get some data from you. So the communication from P2 to P1 or P3, is not needed. And even after that, the all-to-all, it still requires send and receive, and lots of send and receive. You have many communication neighbors, and then wait for the completion of receive for metadata. Is basically the metadata specify what kind of data you actually need, and then the owner of the data would prepare, pack the data, send it back, do these sort of things. In contrast, if we allow active message model, communication model, the model that shown on right, it's much simpler. It's basically P2 just request, make a remote function call to P0, do this. And P0 does not need to, say, post a send or post anything specific a priori. It can just pull in the network. Once it pick up the task, it just executed whatever the task that P2 asked it to do, put the data back, and signal. This would be more similar to your experience of ordering something from some online merchant. For example, you just place an order on Amazon, and they will just ship the package to you, and after you receive, you unpack. You don't have to tell everybody else that I'm not buying things from you, so on and so forth. And the next, I want to show you a little bit about using PGAS for in-node communications. So the one slide that I showed before is mostly for communication between nodes. So PGAS actually is also good for in-node communications. For example, if you just use a pure message passing model, no data is shared. But this is a little bit wasteful because, for example, if you have a shared memory machines, why you do that? But on the other hand, if you use a multi-threaded programming model like OpenMP or pthreads, then everything is shared. But at least on current implementations, often you would suffer from a parallel message injections. So you get very poor network performance if you use a multi-threaded MPI. So ideally, we want to take the both. And then PGAS model can help you achieve that, because in the PGAS model, we selectively cross-map a piece of the memory in the global address space, and then each processor still has the freedom to keep some private data, but at the same time, they can put data into the shared memory heap. Okay. With that, I'll show you some performance. So we first run a communication benchmark called field boundary. So this is from BoxLib, a real application again, but this is just a communication benchmark. So we take the communication characteristics from a real benchmark, but we just measure the communication performance. So this is sort of the best case for what PGAS can do. And we run 3 configurations. One is flat. This is also common in DOE applications, because for people who just want to use MPI or UPC++, just use one model without any additional effort. But also, some other users want to mix with OpenMP, so you can mix MPI with OpenMP or UPC++ with OpenMP as well. The last one is a little bit new. We call it hierarchical. Basically, you use the same model, but handle shared memory communication and internal communication differently. So sometimes people call it MPI plus MPI. If you, from the MPI community, you may have heard of that. Also, MPI shared memory. The same you can do with UPC++ as well. So the bottom line is that even you just pick a single programming model, in this case, PGAS, UPC++, which is on top of GasNet, works the best across the board. That's very important. But of course, I want to know that this is just for particular implementations. It's possible that MPI may get improved in the future, but I just want to show that, by having some independent third-party implementation of some communication patterns, it's good to set the benchmark so that we know what the hardware can deliver. Okay, so the next slide shows you the full application built on top of BoxLib with all the things that I have talked to you about. So this is a compressible actual physics code called CASTRO. So this is end-to-end application, real applications running on NERSC Cray systems. So as you can see here, because this real application involves both communications and computation, so the performance differences are much smaller. But even in this case, if we take the best UPC++ version and compare against the MPI version, you can still see an 18% performance speed up. And that's great, because imagine in the optimal case, if we can shut down the machine after the computation is done, we can save about 20% of the electricity bill. Of course, that's optimistic. But that's great, because if we're talking about supercomputing centers, we are talking about maybe millions of, for electricity bill. That could be a quite significant saving. So next, I want to show you that UPC++ is not only used for application development, it's also used for system software research. A team of partners, research partners at Rice University, Dr. Vivek Sarkar's group at Rice, they use UPC++ and add dynamic work stealing on top of it. So they build something called HABANERO-UPC++. So basically, they have some abstract way to represent the machines and associate some worker threads with each of the locale and use UPC++ to communicate between nodes. And with this, they can achieve very good dynamic distributed work stealing, as I'm going to show you on the next slide. So on this slide, it shows the UTS benchmark using HABANERO-UPC++, unbalanced tree search, 3 implementations, MPI UPC and HABANERO-UPC++. So performance, lower is better, scales all the way to 12K cores, and also achieve low balancing without user intervention. So dynamic work stealing. Okay, and this is summary. Some of the lessons we have learned. So using PGAS and RDMA, it's actually good to change the way how we communicate. So in MPI, you may want to pack, send, and unpack. But in PGAS, especially with nice RDMA hardware, it might be more beneficial to communicate more often with smaller packets. And also, we provide opportunities to move computation instead of data. And that could also save lots of energy used in moving data, transferring data around. And if possible, build some high-level data structures that will hide you from some complexities of the low-level details. And finally, interoperability is very important. And this concludes my talk. Thanks. Oh, and of course, thank you, slides. Yeah. Oh, I have 5 minutes for questions, if any.
So in the slide that you compare async between MPI accumulate, you mentioned that MPI accumulate may require multiple round trip, right?
Yeah.
Could you explain why is that?
Oh, well, of course, this depends on a specific implementations. So this depends on an implementation called FOMPI, fast one-sided, published by Thorsten Hoffler in SC13. So the reason is that we suspect that because they are not, the MPI does not allocate a large buffer for storing the data, because in order to do the remote put and do the updates on the destination, you need a buffer to do that. And in our case, we can allow the user to allocate that buffer in the user level. But in MPI, if it allocates that in the MPI level, it may blows up. So at least that's one suspicion of why they're not doing this remote updates, why they fetch the data locally, do the updates, and send it back. In this case, you don't have to do any remote memory allocation.
Okay, so the assumption here is that the remote side CPU is actually doing the accumulate sum or something. Okay.
Yeah. So it's a trade-off. But again, we want to put this trade-off into users' hand, because sometimes they know what's the best work for them.
Okay, thanks.
Okay.
So what type of interconnects does this run on?
Oh, it runs on all interconnects that GasNet support. So it builds on top of GasNet. So it runs from laptops to supercomputers, including OFI, OFAT. But of course, if you have some specific optimizations, actually it's possible to do some specializations to bypass even GasNet, to directly, say, using a template specialization, if you're familiar with C++, then directly jam in some instructions in the very low level. Yeah, so.
How do you turn this on? So you mentioned this actually doesn't require changes to the language, so it's C++ template?
Yeah.
So is it all open source?
Yeah.
Okay, thanks.
Yeah, thank you. Yeah, oh, there's a link at the bottom. Yeah, all of our work open source by the mandate of DOE. So, yeah.